Swayam Prabha. Digital India. Educated India.
Hello, welcome to the session. We have been discussing the nonlinearities in the charge pump, and one of the nonlinearity in our modeling is that we completely forgot the effect of sampling in our charge pump. Okay, so let us see what it is. So what we have is, if you look at it, in our PFT based PLLs, we measure the phase error at our phase error only once in reference frequency, isn't it? So, we give this up and down pulse, and we have charge pump, so far so good, and this are C1, C2, VCO and so on. So, when both the way we modeled our PFT plus charge pump was that whenever you have phase error, you have phi reference and you have phi output. Whenever you have phase error, the phase error between reference and output, it gets subtracted by the PFT and converted by the charge pump, and you get current which is proportional to phase error, right. That is what we model, but what happens is actually not this. What happens is, when you have phase error between PFT and charge pump, the current comes at the output only once in a reference frequency. If the phase changes between the input and the output during the reference period, right, that particular phase error is going to be, whatever phase error you accumulate, that phase error is going to be entertained in by the PLL loop only during the next reference cycle. So, if I want to write, it is like PFT operates only on positive edges of or rising edges of the clock. It does not operate in between. Okay. It operates like that. There is no feedback. Once you get the rising edge on the reference and the rising edge on the VCO, once you get this phase error is taken into account. After that, even if the VCO frequency drifts or anything happens there is no feedback between two positive edges. Okay. So, if your V edge has changed here, because of this you are changing, then it is like until the next V edge comes, you are not going to do anything, okay, whatever happens to the VCO. Another thing is, there is, you can say, a one reference clock cycle delay. You change anything in the charge pump, right, if there is any disturbance or anything in the charge pump of PFT, it is going to be, if it happens during the current reference cycle or before the rising edge on the reference or the output clock, it will be taken into account. Otherwise, if it happens after that, it is going to be taken into account only in the next reference clock cycle. So, there is like a one reference clock cycle delay. Okay. So, what we are doing in our modeling is the following, that what we are doing so far, we are actually sampling our system in the real PLL. right. We are not having, if you look at it, I mean, so I did approximations initially using z domain transfer function, writing difference equations and so on, but those were approximations. Okay. When you look at your actual PFT, what we are doing here is the following. We are having our reference phase and our output phase, and or output or divided phase if there is a frequency divider, and whatever value it gives, right. We are sampling this. Effectively what we are doing is we are sampling in our system at reference rate. Our actual model is, or you can say a model which is closer to our PLL operation is this rather than this. This is not the exact model. Okay. The exact more accurate model is this one. You can get phase error, but I will sample the phase error only at the reference rate, right. So, when you have such kind of PLL in the system, so what field which you are using, so let me just do it how we will analyze, or can we still continue with our modeling which we have been using. Okay. So, let me just remove this and say a more accurate model for our PLL is the following, where you can have the phase error between input and output, or the reference and the output. It gets multiplied by your gain, by your PFT gain KPD, right. It gets multiplied and you can have your charge pump, okay. And this is actually a sampled version. So, you sample at reference rate by your reference clock. You get from your PFD, you have the phase error, then that particular whatever input and output phase error you have, phi output, by the way this is out here rather than VCO, you have phase error between reference and output. That particular phase error, your PFD gives a proportional value, right, and that particular phase error is sampled, and it is sampled at the reference rate. And this is something which we have seen. We ignored it at that time, we approximated it, but now it is the time to see how far our approximations were valid. So, what happens here is, in this particular case your ICP changes only at fixed intervals, and that is how you change your control voltage and so on. So, there are multiple or you can say a couple of methods to analyze such kind of systems. Okay. One of the methods is impulse invariance method to analyze such a PLL. There is an important conclusion after this our discussion. So, let us look at it how we arrive that conclusion. Impulse invariance method. In this method you can say, I want to find the loop gain of this system. This is like you have R and C, right, and you have a sample value. So, what you will do is you will apply an impulse, right, and you do all sampling and everything, and you see what comes back in time domain. Okay. So, when you apply any change at the input and you see what comes back in time domain, that is effectively what you are doing here is you are looking at samples, time domain samples of the loop gain. Samples of loop gain, and that is something which you are calculating using the exact operation. Okay. So, you calculate time domain samples of loop gain, I will say that they are loop gain of t. okay, and you pick up samples, pick samples at regular intervals from this because loop gain of t, when you are going to apply an impulse, you will have an actual you will have a real signal as a function of time. For example, just to tell you, if I have loop gain, this is just a loop gain of t in my real system, right. What I am going to do is, I am going to sample that at fixed rate, which is my t ref. Okay, because that is what is happening in the system. I am sampling my loop gain signal at fixed intervals t. So, pick samples for loop gain of t at t equal to n times t ref. Okay, so, you get the samples for the loop gain at n times t ref. Now, you have discrete loop gain samples at t equal to n times t ref. These samples I can use to calculate loop gain of z. Okay. So, you calculate loop gain of z. So, this is going to be a z domain for the loop gain, and then you analyze your closed loop system. So, when I go ahead and do all such things, you will be surprised that the actual loop gain expression in our case, using making sure that the sample values are from the actual system, the loop gain of z is going to be k times z square into C1 into 1 minus a divided by C1 plus C2 plus 2 pi by r C1 omega ref. Omega ref is your reference frequency, right. This is the coefficient of z square minus z times C1 into 1 minus a divided by C1 plus C2 plus 2 pi r C1 omega ref times a. Okay. Well, you can always refer to the papers which was published this. Z cube minus z square times 2 plus a plus z into 1 plus 2a minus a. Okay. And here a is equal to exponential of minus omega p3 t ref. Omega p3 is same 1 over r C1 by C2, C1 C2 plus C1 by C1 plus C2, and k is equal to KVCO times ICP r C1 divided by omega ref into C1 plus C2. Okay. So, while using the sampled values of the PLL and finding the loop gain from there, the loop gain happens appears to be like this. This loop gain we were earlier we were approximating as, just to tell you how simple, we were using ICP over 2 pi KVCO over S square C1 plus C2 into 1 plus S by omega z divided by 1 plus S by omega p3. This is what we were using, but the actual expression is this. Okay. Now, you can very well find the bandwidth while using these omega z transfer function. What you are going to see is the following. First, if f ref by f bandwidth, or you can say unity gain frequency for the PLL loop. So, we have found earlier omega u. Okay. So, let me write it this way, omega ref by omega u, right. If this is greater than equal to 10, okay, then our Laplace domain or continuous time Laplace domain or continuous time analysis holds to a good approximation, and we have verified this by getting the actual plot or the response, comparing your Laplace domain response with your discrete time modeling. As omega ref by omega u reduces, okay, omega ref by omega u reduces, that can only happen when omega u increases in comparison to omega ref. When omega ref by omega u reduces and approaches values lesser than equal to 3.5, these are the calculations that you will see, lesser than 3.5, you will find that the systems becoming unstable. The system starts becoming unstable, and what happen is that you will start seeing the closed loop poles in the Z domain analysis going outside unity gain circle, okay, which is the condition for instability. So, as you see, the condition for instability in case of Laplace domain or frequency domain analysis, Laplace domain analysis is that you have poles in the right half plane. Similarly, in Z domain analysis, if the poles are outside unity gain circle, then the system will be unstable. So, as this ratio of your omega ref by omega u reduces, then what you will have is that your output frequency, that your poles will start going outside unity, closed loop poles start going outside unity gain circle, and you will lose on the stability. So, as a rule of thumb now, I will not say that if your unity gain frequency exceeds omega ref, then your PLL will become unstable. No, that is not the case. In many implementations, we can implement our omega u greater than omega ref by 10. We have implemented omega ref by 8 and even higher, right. But the thing is, the matching between our this transfer function and our discrete time transfer function will not be there anymore. Okay. So, if you are implementing your PLL with unity gain frequency which is less than equal to f ref by 10, you can very well be assured that your continuous time analysis or Laplace domain analysis is quite accurate to model this sampled system. If your reference frequency, if your unity gain frequency, if omega u is greater than omega ref by 10, right, accurate modeling requires Z domain analysis. Okay. Please do not use Laplace domain analysis or the continuous time analysis which we have done. Okay. If omega ref omega u becomes much larger than omega ref by 10, okay, or it approaches, you can say even omega ref by 2 or something, the PLL will become unstable. PLL shows instability because your closed loop poles go beyond the unity gain circle. Okay. So, keeping this in mind, we will design our PLS. Okay. Thank you.